就是 Untitled 嘛，就是 unarmed non-white shot 跟 unarmed white shot。所以我就想，因为这边你 softmax 嘛，它然后我就会拿unarmed shot for white， 就是unarmed shot for non-white， 就是从用 stat 方式说，拿第二个号码，然后这个就是它的。
就是它就是这个里边
对，这个是 rate， 然后我们要3000个嘛。
就是3100个，就3000乘以1个 matrix。
3000乘以1，但是如果你能够首先你设1000就是3000乘以1000。
Okay, let's get going. Lots to learn. Before we get started with the matrix algebra and stuff, are there any other questions about the homework due on Thursday? I kind of messed up and uploaded the one that from 2016 that I kind of based the GSS question on instead of the 2019 one, and I didn't fix it until Saturday. So make sure you download the right assignment 4 from Canvas. But if you already spent some time trying to develop a model on the GSS, that'll be basically applicable to what you need to do with problem 2. Problem 1, there's been a lot of questions about on Campus Wire and stuff, which is fine. But there's a lot, I think, of sentiment that, oh, well, I understand what's going on with this paper, but I can't write it in SAN code. And that's not going to cut it. Basically, the only way you can sort of satisfy a sufficient condition for demonstrating that you understand something is if you can reduce it to a series of steps in code that have the probability distributions and everything like that. Once you got into that state, then you understand the model well enough to condition on data, to update your beliefs about it, to say, I think this model is wrong. I want to do something different with the way it is, but just sort of saying, okay, I have a vague sense that this is a model about police shootings, and what the guy found was that people who are black or Hispanic are much more likely to be shot than people who are white. Okay, yeah, that's the main conclusion of it, but that does not sort of demonstrate you understand the model that he chose to estimate with enough detail, with enough precision to actually be, able to operate on it from a social science research perspective, as opposed to just I understand the title in the abstract sort of thing. So to really understand the model, you have to be able to write the code that characterizes the model. So anyway, other questions about that? Okay, so this week we're going to start talking about vectors and matrices. We've put this off as long as we can into the semester, but it's now sort of starting to impinge on our ability to talk about models if we can only sort of refer to scalars. And really, what's going on, although it's not obvious to the user, what RStanArm and BRMS are doing is just basically getting a matrix algebra representation of the model, and then we have a Stan code that's written in terms of these vectors and matrices that just runs, and then there's R code that makes it into the data into vectors and matrices, and then passes it up, and we get back matrices and vectors of stuff back. So really all we're doing is using the stand language to manipulate those things, and so we need to learn a bit more about them. Of course, after clarifying the fact that as members of the Columbia community, which gets lots of money to develop Stan, and using Stan outside of Columbia creates the grounds of conflict of interest, as you know about. Not actually going to talk about Stan that much today, really just sort of taking a math perspective on matrix algebra. We will refer to Stan a little bit. Okay, so just basics of notation. Some of you have seen this before, but anyway, a vector is collection of scalars, a container holding scalars. And most books will use the convention that a vector is written in lowercase but boldface font. So X here, specifically X in this case refers to a column vector, which is oriented up and down. So it has x1 in the first position, x2 in the second, xk in the last position for a vector of size k. And the transpose operator, which I will write with a capital T superscript. Some people write it with the prime symbol superscript, but I'll use the T. Changes the orientation of a vector from a column vector to a row vector, or from a row vector to a column vector. So in this case, X transpose is oriented horizontally. But most books in computer languages and whatever, if you just refer to vector, that means a column vector. And if you want to specifically refer to a row vector, then you transpose it explicitly. Same idea is a little bit more general with matrices, which can be thought of as a two-dimensional container, a collection of row vectors or a collection of column vectors. And the column vector contains scalars, so indirectly a matrix is a two-dimensional container of scalars. But if you think about it as a collection of row vectors or column vectors, those row vectors all need to be of the same size, or column vectors. Matrices tend to be written with capital boldface letters, capital X here. So that is a little bit different from the notation that we've used before, where capital letter means random variable and lowercase means a realization of a random variable, but there's just not enough different symbols to be able to make everything unambiguous. And a lot of this matrix algebra stuff goes back to when they were writing it on typewriters and whatnot. So when they needed a distinction, they did the capital thing. And so that is the convention we'll follow. In general, this X, you could think of it not equivalently, but in some cases you can think of it as a collection of random variables. And in other cases, you can think of it as a collection of numbers. It could be realizations of random variables, could be stuff that you condition on. So anyway, the uppercase, lowercase distinction here pertains to whether it's a matrix or a vector, not whether it's a random variable or a realization. We can refer to columns or rows of a two-dimensional matrix with one subscript. So X sub P here indicates the pth column of X. Also, we can think of the transpose operator as, so if it's X transpose, we can think of that as transposing each column of X. That has the effect of switching the column index with the row index for each scalar in our matrix. Also, when necessary, but I won't often use this, if I have X transpose with one subscript, that indicates the kth row of a matrix. There's not a great way, if you just have one subscript, to say, is this referring to a column or a row? Could be either one. So I will use the convention, if it's referring to a row, I'll put the transpose in there. Otherwise, no transpose, it's just referring to one of the columns, the p column, etc. Questions so far about this notation we're using, and also the same in the book? Okay. So let's just get some of the easy stuff out of the way with vectors and matrices from the beginning. So any function that takes one argument can be applied to the elements of a vector or a matrix to produce another vector or matrix of the same size whose elements have had the function applied to them. So if you do like the logarithm of a vector, what comes out is a vector of the same size of logarithms for each of the scalars in the thing. Now, that's technically the element-wise application of a function. There is such a thing as like cosine of a matrix that's distinct from like a matrix of cosines, but we're not going to get into all of that. So you can just think of single argument functions as being applied element-wise to elements of a vector or a matrix, and that's consistent with how it's done in Stan. Also easy, any vector or matrix can be passed to a function that accepts one argument and outputs a scalar in a pretty unambiguous fashion. So like sum, prod, various matrix norms and stuff like that that output a scalar. Those are pretty straightforward. So the sum of a matrix just sums up all the scalars in the matrix, outputs a scalar. Multiplying a vector or a matrix by a scalar is sort of equivalent to dividing a vector or a matrix by a scalar if we just take the reciprocal of the scalar. So multiplication and division are about the same thing. And multiplying a vector or a matrix by a scalar yields another vector or matrix of the same size that contains ratios of the original elements of the vector or matrix divided by or multiplied by the scalar. And so you get out a matrix of the same size that has either products or ratios as its elements, and division by a scalar is basically the same as multiplication by the reciprocal of the scalar. So that is all pretty straightforward. Adding and subtracting a scalar to or from a vector or matrix works in a similar fashion. You get back a vector or matrix of the same size whose elements consist of the sum or the difference between the elements of the original input matrix and the scalar that you're adding to that vector or matrix. Also, conceptually straightforward, adding or subtracting two vectors or matrices that have the same size results in a vector or matrix of the same size whose elements are the element-wise sum or the element-wise difference between the respective elements of those two vectors or matrices. But the fact that we're supposing here that the two vectors or matrices are of the same size is necessary to have addition or subtraction of two vectors or matrices make sense. Otherwise, you would have, if like one matrix was bigger than the other, you would have leftover elements, and like, what do you do with them? Addition and subtraction of the two vectors or matrices requires them to have the same size. And if you're adding a scalar to a vector, then implicitly the size of the vector controls the size of the output. Finally, element-wise multiplication or element-wise division between two vectors or matrices of the same size, yielding a vector or a matrix just like in the addition or subtraction case. But now the output matrix, its elements are going to contain products or ratios of the corresponding elements of the input vectors or matrices. And so that's all pretty straightforward, but that's not usually what we mean when we talk about matrix multiplication. And so if that's what we mean, we need to say specifically element-wise multiplication, also sometimes known as the Hadamard product, as opposed to the regular product of matrices, which is more complicated and we'll talk about later. But for now, are there any questions about these less complicated operations on vectors, matrices? Yeah, and you know, all of this is consistent with how it's treated in R. There's some differences between R and stan though. So in R, they don't really have a distinction between a column vector or a row vector. They just have like vectors, and R for the most part will sort of figure out whether you intended it to be a column vector or a row vector based on which orientation makes sense. But in stan, they're actually stored as different types of things, and thus they have different keywords. So vector and row underscore vector, they're both one-dimensional things of size k, but vector you can think of as oriented horizontally, vertically, and row vector being horizontally. So that type distinction is more important in stan than in the R language. In R, you can have vectors and matrices of integers, and they're stored as integer vectors or matrices, etc. But in stan, row vector, vector, matrix all implicitly contain real numbers. So you can fill it up with integers, and that's fine, but they're going to be stored in double precision anyway, as opposed to two-dimensional or one-dimensional or multi-dimensional arrays, which can contain integers and are stored as integers. So sometimes in stan you have to use two vector, two row vector, two matrix, etc. to coerce something from, you know, whatever it is currently to a matrix or whatnot. Those work similarly to the as dot vector, as dot matrix functions in R. R uses the T function to indicate transposition of vectors or matrices, whereas in stan, the corresponding function is actually spelled out as transpose, which is like a 9-letter word. So you can just abbreviate the transpose operation by putting an apostrophe on the end of a vector or a matrix. So that's much faster to type, but it's like hard to read because the apostrophe is so small relative to the other letters. But anyway, stan also has some special types of vectors that are not available explicitly in R, like a simplex, which is going to be a vector of size k, whose elements are non-negative in sum to 1. Also has a unit vector of size k. I'm not sure we talked about a unit vector in this class before, but we say x is a unit vector if and only if the sums of the squares of the elements of x are equal to 1. So the individual elements can be negative, unlike a simplex, but their squares sum to 1. And so basically, if you square up that unit vector element-wise, then you have a simplex. Questions about those? Okay. So vector multiplication, otherwise known as the dot product or the inner product. So this is where things start to get different from what you learned before in terms of scalar algebra. But if you take or go to a seminar like the ones that they have in here like every 3 weeks, or some advanced math classes, or just generally when you hear someone say, I'm going to start doing some weird math, the first question to ask is, okay, in your weird math world, how is the inner product defined? And that's just like the key to understanding all weird forms of algebra. Matrix algebra, I wouldn't say is a weird form of algebra, but the definition of a vector product is fundamental to that algebra, and so we need to understand the definition of it. So if x and y are two vectors, both of size k, we define their vector product as x transpose times y. So now x transpose is a row vector, y is a column vector, and their vector product is defined as the sum of the pairwise products of the elements between those two vectors. So a vector product does not output a vector. It inputs two vectors, outputs a scalar. You can think of a vector product as being element-wise multiplication of those two vectors followed by summation of the resulting vectors, so you get a scalar coming out in the end. And that's what makes vector multiplication fundamentally different from scalar multiplication. So in R, you can do transpose X percent sign star percent sign Y in order to indicate vector product of X and Y, or you can do cross prod, T cross prod, other things like that. In Stan, there's a dot underscore product function, which will accept two inputs, like irrespective of whether they're row vectors or column vectors, and it will output a scalar that results from the element-wise products followed by a sum. Or you can just do X star Y if X transpose is a row vector and Y is a column vector, and that will work. So in other words, Stan uses the same symbol, the asterisk, for both scalar multiplication and vector multiplication. It uses a different symbol, dot star, if you want to explicitly do element-wise multiplication, which is more rare. So a common construction, a way of that you'll see a lot, is some vector transpose vector multiplied with itself. So X transpose X, which can be written as the sum of the squares of the values in the vector X, and that construction has a special function in Stan called dot self. So it's basically the dot product of X with itself, and you can simplify the implementation of that function if you know it's the same vector on like the left and the right side. So it only has to input one argument to it. It has a simpler and faster implementation. The length of a vector of size k is defined as the square root of the sum of the squares. A lot of times people, if they're not really having a linear algebra background, will sort of be ambiguous whether they're referring to the length of a vector or the size of a vector. So the size of a vector, properly speaking, is an integer, like k. How many elements are in this vector? But the length of the vector from sort of a geometric perspective is going to be a real number, and is defined as the square root of the dot self of X. And that's especially confusing if you come from R, because length of X in R just returns the number of elements, which in this case would be k. It's safer in R and less confusing to use nrow to refer to the size of a vector. And in Stan, it's actually that corresponding function is called rows or cols, if you want to refer to the number of columns in a matrix. Number of columns of a column vector is just one. In general, you can think of a row vector as being a matrix with one row, or a column vector as being a matrix with one column. But in Stan, they're actually stored slightly differently, so it'll work. But usually, if you know something is going to be specifically a vector, declare it as a vector rather than a matrix with one column. That's in contrast to MATLAB and Python and some other things. So questions about the vector product? Like I said, if you've seen it before, it hasn't changed. If this is the first time you've been exposed to matrix algebra, this is where it starts to get different. Yes?
Can you give more intuition about the length of the vector and why it's the square root of the product?
That's just a definition. The definition corresponds to the geometric interpretation of vectors in this like k-dimensional space. However, the geometric interpretation of vectors isn't particularly useful for Stan or statistics. So we're emphasizing the algebraic nature of vectors. There's also like clever representation of matrices and whatnot in terms of graphs, which like it's clever, but I've never really understood how that would help someone do something in Stan by having like a thorough understanding of the graph representation of like a matrix. So I haven't talked about it. Anyway, we're just emphasizing the algebra, in which case you can understand as the definition, the length of a vector is the sum of the square root of the sum of squared elements. So it's going to be positive, but a real number, as distinct from the size, which is just an integer. And these vectors need to be declared with a size so that Stan knows how much memory to allocate for them. But length is just like a function you could evaluate that function. Anyway. Okay, so matrix multiplication is basically seeing a matrix as a collection of vectors or row vectors and doing repeated vector products among those things. But it's kind of a mouthful. So if we have a matrix X, which has k rows and m columns, another matrix Y, which has m rows and p columns, then we define the product of matrices X and Y as the new matrix Z. Z is going to have k rows and p columns, such that its elements are defined, as the element in row K and column P as the vector product between the kth row of X and the the pth column of Y. So we take out the kth row of X, and then we take out the pth column of Y. We vector multiply those two things together. We get a scalar. We put that scalar in the kth row and pth column of Z. We do that for all rows of X and all columns of P, or all columns of Y. And we get back k times p scalars, each put in the corresponding cell of the resulting matrix Z. So matrix multiplication is basically doing a lot of vector multiplications. But just to say it again, if we have a matrix X that has k rows and m columns, a matrix Y that has m rows and p columns, the matrix product is going to be a new matrix that has k rows, p columns, and each cell is filled by doing a vector product of some row of the matrix on the left with some column of the matrix on the right. Doing that for all rows and columns fills up Z with those scalars. So as hopefully is apparent from the definition, matrix multiplication, unlike scalar multiplication, is not in general commutative. So X times Y is not generally equal to Y times X. Indeed, X times Y, if that's defined, Y times X might not be defined. Because in order for two matrices to be eligible for multiplication together, it has to be the case that the matrix on the left has the same number of columns that the matrix on the right has rows, in order for there to be the right number of vector products to fill up the resulting matrix Z. Now, if both X and Y have the same number of rows as they have columns, then both X times Y and Y times X are defined, but in general, they're going to be matrices that have different numbers in them, because the vector product is not invariant to the order in which the things are on the left or the right. So matrix multiplication, like a lot of multiplications out there, but unlike scalar multiplication, is not commutative. addition and subtraction and whatnot of matrices, or addition of matrices is commutative, but multiplication is not. It is, however, the case that x times y quantity transpose is equal to x transpose is equal to y transpose times x transpose. So the transpose of a product is equal to the product of the transposes in reverse order. So that is sometimes an important thing to use. Another common construction you'll see, particularly in regression models where X is a matrix of predictors. Let's say it has n row and k columns, and we want to multiply it by a column vector beta that has size k. We can think of that as a k by 1 matrix, and so n has the same number of columns as beta has rows. These are good for, or eligible for multiplication. We say they're conformable for multiplication, and the result is going to be an n by 1 thing, which is to say a column vector, which we'll call eta, or if this was like a Gaussian model, we'd probably call it mu. But anyway, eta as the product of the matrix X and the vector beta, and so we just take each row of X, vector multiply it by a common coefficient beta. Each time we do that, we get a scalar. We put that scalar in the corresponding row of the eta vector, and we formed our linear predictor for this model by multiplying the predictor values by the coefficients. And if you expand it all out, we see the form that we've seen before in this class, and you've probably seen before in other classes, where the linear predictor is basically a weighted sum of the predictor values using the vector of coefficients as weights, and using the same weights for all rows of X. You get this, first predictor times first coefficient plus second predictor times second coefficient plus, last predictor times last coefficient to form that linear predictor, which can be contained succinctly in a vector of size n. Questions about that? Okay. So having vectors in matrices allows us to write much better, which is to say much more general code to draw from a prior predictive distribution of a generalized linear model, or in this case, just a plain linear model. So what we've done a lot before without having matrices, or without using matrices, is I would just say, okay, X is some vector. And then I say, okay, this is easily extendable to the case where you have more than one predictor, but I'm just showing you the case where there's one predictor. Now, if I can define a matrix X, it can contain as many predictors as I want. So my stand function, I'm going to define lm underscore rmg as a function, and this function is available in the stand program on Canvas. It's going to take an integer s for the number of draws of the prior predictive distribution that I want. A matrix X, which is n by k, it's going to have the predictor values for all k of my variables. I'm going to have some prior about the of the intercept and the coefficients of our k into the scale, the expectation of the segregation of errors. As there, we can convert from rows and we don't have